Again, we've been talking about transition metals, complex ions, coordination compounds. Um, so we talked about naming them last time or a couple times ago. We also talked about how to write the formulas. In addition, we sort of finished up last time talking about isomers. And so remember, isomers really are really the same sort of formula. There's some type of different connectivity. That different connectivity also gives them some different sort of properties from one another. And also can make some of these isomers what are referred to as being chiral. And that means that basically they have a mirror image that is non superimposable. So last time we saw a couple of examples there where you kind of slap something up to a mirror, and the reflection that's coming back to you is either superimposable or non superimposable. And again, if it's non superimposable, that's what's referred to as being chiral. Again, kind of like our hands. If you put your hand up to the mirror, you get basically the reflection of your other hand. If you take that reflection out of the mirror, again, in terms of your hand, no matter how you sort of rotate it, move it around, you can never really get the mirror image and your original hand to basically sit on top of each other correctly. Again, as we talked about last time, you'll have either like a thumb in the wrong location, or you'll be palm up, palm down. That won't be correct. There's always something that's a little bit different. And as we saw in some of those, it's just that reflection into the mirror, which attaches certain bonds, it's just slightly different. And again, we get these guys that are non superimposable. So, what we're going to finish up talking about is sort of in a sort of complex ion situation, how the electrons get sort of distributed, especially the electrons on the central atom, which again is usually like your transition metal or positively charged sort of cation. So we're going to see how those guys get really distributed in the presence and sort of, really in the presence of ligands, but also, sort of how it compares to if there was sort of no ligands sort of present. Now, when we have these ligands sort of bind in our complex ions, they do form sort of geometry, kind of similar geometry that you probably learned when you're talking about Lewis structures and things like that. Um, so let's talk a little bit about that and sort of the hybridization idea. The formation of hybrid orbitals to share electrons. So if you remember, perhaps when you talked about bonding, you talked about things like hybrid orbitals like sp, sp2, sp3, sp3d, sp3d2. And again, the idea, just briefly, right, to remind you about sort of the hybridization model, was that it does sort of account for those sort of geometries that we see in molecules, the bond angles that we do see in molecules and stuff like that. What is a hybrid orbital? Again, it's basically a combination of two atomic orbitals. So when we talk about atomic orbitals, those are like your s orbitals, your p orbitals, your d orbitals. And basically the idea behind sort of the hybridization is that, if you try to mix a p orbital with an s orbital, they're different shapes. They're also different sort of energies and things of that nature. So the idea of hybridization makes these orbitals, which are really sort of a mixture of those guys, and they have kind of the same shape. They also have sort of the same energy sort of situation that they're at. And again, it allows for sort of better bonding to occur. Now, although it doesn't work perfectly for complex ions, we do sort of apply some of the aspect of that to our complex ions in terms of sort of geometry and things like that. But again, the interaction in terms of sort of the ligand and the metal is really more viewed as more of an acid base sort of model. And that's more like your Lewis acid and your Lewis base model, like we've been talking about. Again, a Lewis base being something that will donate a pair of electrons, and a Lewis acid is again something that will accept a pair of electrons. And that's why our sort of metal in the middle of our complex ion has a positively charged, usually a fairly good positive charge, that also kind of fits in that Lewis acid situation because it is electron deficient, right? So things with positive charges definitely have less electrons and are electron deficient, willing to accept those electrons. And that sort of fits very nicely. And when we talk about sort of the hybrid orbitals, again, sort of applying it to our complex ion, it does depend on sort of the number of ligands in terms of sort of the geometries that we associate with these guys. So if we think about something like 6, sp3d2, and sometimes people will write it like this. Sometimes people will write the hybridization sort of like this, sp3d2. And it's basically, in this case, if we look at this cobalt with our 6 sort of ligands attached, it's really going to take on, if you remember, for kind of Lewis structures, 6 electron pairs. That's that octahedral sort of geometry, and it's going to take that sort of octahedral arrangement. Again, here we could see our NH3s going to be donating its pair of electrons. Again, our electron deficient cobalt going to be accepting those guys. Now, there's several sort of geometries that we associate with these sort of complex ions. Tetrahedral, and again, kind of similar to Lewis structures and stuff like that. If you just kind of look, that's like 1, 2, 3, 4 ligands attached. So that's like your tetrahedral sort of arrangement. But we could also have this more square planar arrangement here. Also has 4 ligands attached. This guy, though, has slightly a different hybridization than this one. This is sp3, which, goes with tetrahedral. This sp3d hybridization kind of goes, our sp3d2 hybridization, goes with that square planar geometry that we sometimes see in that expanded octet that we see with our octahedral arrangement, get our square planar sort of geometry. Here's a couple of ligands attached, so our kind of sp hybridization happening, just like what we see with our linear as well. So based on the coordination number, we do typically get these sort of geometries that occur with our kind of coordination numbers and our complex ions. And again, you could almost relate it similar to what you did with Lewis structures. Again, if you think about kind of 2 electron pairs, that's linear. I got like 4 electron pairs, that's tetrahedral. Again, our square planar being more of that expanded octet type of situation, and then our 6 electron pairs being octahedral. So similar type of idea as to the geometries that we see associated with these complex ions. Questions on that there? Okay, so now what we're going to talk about it is sort of the idea of what happens with those electrons that are in these metals that's in the center of these complex ions, and sort of how these electrons get distributed. And it really does also depend on the ligands that are there, which ligands are attached, as to sort of how we see electrons being distributed. So let's talk a little bit about that sort of binding that occurs in a coordination compound, or really a complex ion. And these are our 5d orbitals. So again, these are just like from electron configuration, are 5 different d orbitals. Obviously, each orbital could hold 2 electrons, right? So in the absence of any ligand present, all 5 of these d orbitals will essentially be at the same energy level. So in the absence of ligands being present, the d orbitals there in our complex ion sort of, I guess it wouldn't be a complex ion, the part in our metal are going to be all the same energy. But what happens though when we start to get ligands being attached, there's actually a shift that occurs, or a splitting that occurs between these d orbitals. And these are the d orbitals in our transition metal. That's basically in the center of our complex ion, right? So it's basically our metal here in the center of our complex ion. And what's happening here, and what we're looking at here, is actually the splitting that occurs really with a coordination number of 6, sort of that octahedral splitting. So what ends up happening is we get these two d orbitals, these two guys right here, kind of your squares, if you will, that actually ends up going higher in energy than these three d orbitals. They actually end up sort of lower in energy. And you may say to yourself, well, is that a sort of a big deal? And it is sort of a big deal when we think about how these electrons sort of populate, if you will, right? In a normal situation, electrons will populate one at a time, right? And then come back basically and pair off and all that good stuff. So if these five sort of orbitals split off from each other and some are higher in energy, some are obviously lower in energy, it will affect basically how these electrons go in. You know, they may go this way and then decide, well, that difference is not all that much. We'll just continue to kind of feel like normal and so forth and kind of pair up everybody. Now, there could be a situation that we'll talk about here in just a second where the opposite sort of happens, which means, you know, obviously electrons go in lowest energy first, so they go in. And then when we get to that fourth electron, he's going to look and go, whoa, those guys are like way too high up there. I would rather go this way first and pair up here and then maybe go up here if I'm forced at that point. So, as we'll talk about, that difference between sort of the lower set of d orbitals and the higher set of d orbitals, which is what is referred to as the crystal field splitting. So, that difference here between these orbitals is what is referred to basically again as that crystal field splitting. It's sometimes abbreviated with a delta sort of symbol. It's basically the energy. It's that energy difference between the lower d orbitals and the higher d orbitals. And again, depending on how big that split is, it will affect whether or not, you know, we get a lot of paired electrons, a lot of unpaired electrons. Things are paramagnetic, you know, has a lot of unpaired electrons depending on that split. So, how do we calculate something like the crystal field splitting? Well, you know, we can basically use the regular sort of equation that maybe you learned back in 1B. This is something that we've seen before, sort of maximum absorbance, right? Value here. Remember, we always want to pick at the top of the hill here so that all of our samples basically give an absorbance value. That is basically the same one as our E is equal to H times the frequency, H being Planck's constant. That's our 6.63 times 10 to the minus 34 joules seconds. That is the frequency, usually in reciprocal seconds. And that is also related to C is equal to the wavelength times the frequency, C being the speed of light. That's probably an equation you might remember from last semester. Obviously, this is our wavelength, usually in meters. Speed of light is meters per second. It's actually 3 times 10 to the 8 meters per second. That is, again, our frequency in reciprocal seconds. We could use this relationship and this relationship and solve for frequency. Frequency would equal C divided by the wavelength, which means we could also add into here HC divided by the wavelength, which means, again, if you just kind of know the wavelength of light, you can figure out the energy or the crystal field splitting that's going to sort of happening, as H is a constant, Planck's constant, and C is a constant, which is the speed of light. So, you know, we could actually calculate this splitting that occurs and figure out, you know, how much energy per mole there is between the lower d orbitals and the higher d orbitals. So let's take a look at an example of that, and I think it might be worked out on your page. So we'll kind of go through the calculation just to make sure here. of what's going on. I'll talk about it. So in this particular case, with the absorption maximum for a complex ion for our cobalt with our 6 ammonias attached there occurs at 470 nanometers. What is the color of the complex and what is the crystal field splitting that we would expect in kilojoules per mole? So a couple of things to remember from some of the conversations we had earlier on in the semester as well, especially in lab. We talked about the idea that the color that we see, for example, of a solution is really the complementary color, right, to what is being absorbed, say, by the spectrophotometer. So in this particular case, if the maximum absorption is happening at 460, that would be in this region. To us, the solution would appear to be its complementary color, which is right here across the way, and that would be orange. So remember that, as we talked about before, sometimes people are surprised by that. They think, well, I see a solution that's orange. I should clearly set my wavelength in the orange region, and that would be incorrect. So remember, what's being absorbed is complementary color to what we actually see, say, in the solution or the test tube. So in this case, again, because it's absorbing in that bluish range, we would expect, again, that sort of orange appearance for our solution and our complex ion to be more of an orange. If it happened to move into this range here, the purple region, it would appear to us in terms of color be yellow and so forth. Now, how do we figure out the crystal field splitting in kilojoules per mole? Again, this is basically the equation that we just saw there. E is equal to h times the frequency. Again, substituting in for our frequency, the speed of light over the wavelength. We would do this because in this case, obviously, we are only given the wavelength. So we do have to do a few different conversions. Again, this number right here is Planck's constant, so that is h. This is our speed of light. And again, because really our speed of light is in meters, this guy is in nanometers. That is what this part of it is, the times 10 to the minus 9. That's converting from nanometers to meters in that case. And that gives us 4.23 times 10 to the minus 19 joules. And really, when we solve for that, that is joules per atom. We're looking for kilojoules per mole. So we have atoms and moles. That is why we then take Avogadro's number there. So again, we're going to use Avogadro's number as a conversion factor, really to go from atoms to moles. And a reminder, hopefully we remember our good friend Avogadro, 6.022 times 10 to the 23 atoms per mole. That will get rid of our atoms. And if we just look at units, that is joules per mole. And then obviously we could do our conversion between 1,000 joules and a kilojoule. That will ultimately get us to kilojoules per mole. So that's how we do get down to this number right here. So this splitting, again, we see a coordination number here of 6 like we've been talking about. That's that octahedral splitting that we're going to see, where we will have those 3 lower d orbitals, those higher d orbitals. Again, what we just calculated is the energy difference between those two. It's about 255 kilojoules per mole. Any questions on that calculation there? So you may also be asking, well, how do I know, if the electrons are going to go in, how do I know, are they going to go to the top? They're going to go to the bottom. The splitting is too big, it's too small. So there is a way that we could kind of determine whether or not sort of the splitting that we will see is going to be a sort of large splitting or sort of a small splitting that's going to occur. And it is going to basically be determined by, excuse me, going to be determined by the ligands that are attached. So there's a spectrochemical series here of ligands, and that's what we see on the bottom. And to the left, we have ones that are referred to as weak filled ligands. And to the right, we have the ones that are referred to as strong filled ligands. So what does each of that mean? Well, weak field means that when you have those ligands present, the splitting that we see between the lower d orbitals, for dramatic purposes, I'll draw it like that, and the higher d orbitals is going to be a really small sort of value or small difference. And what that affects is when we would distribute the electrons, and again, here we're talking about the electrons that are on the metal, we would distribute it like normally distributed in electron configuration. We would do one at a time and then come back and start pairing off everybody, obviously continuing this pattern all the way across. Now, if we're more on the right-hand side here with these strong field ligands, so this would be a weak field, we would have a much larger split that's going to occur. I'll do dramatic drawing there for purposes of our d orbitals. So we have this really kind of larger split. And when we have this sort of larger split, what's going to happen is when the electrons decide to sort of populate these d orbitals, what's going to happen is they will go this way, they'll go this way, they'll go this way, and decide, no thanks, that looks pretty big, and decide to fill up down low first, and then head upward there if necessary to do so. And in this particular case, when we look at the difference, this is, by the way, what is again a large split, and this is what is referred to as strong field. What is sort of the difference between sort of our weak field and our strong field in terms of how the electrons are populated? Well, what we see is we have a lot more unpaired electrons happening there in our weak field versus our strong field distribution. And a lot more unpaired electrons gives us sort of paramagnetic, and we get, you know, a lot more spin sort of happening in this particular complex ion. Now, when we look at this sort of guys, you also may be wondering kind of like what happens in the middle. So sometimes in the middle, they'll ask you to do it for, strong field, or they may ask you to do it for weak field. So they'll kind of give you maybe some hint as to what to do. Occasionally, they may not even tell you, and it may not make a difference. And what I mean by that is typically in these type of questions, they very typically ask about, how many unpaired electrons, are there in this particular complex. And what I mean by there may not make a difference is when you go and sort of distribute your electrons, it may not make one difference depending on how many unpaired electrons. You may get like one unpaired electron in both situations, may get no unpaired electrons in both situations, regardless if you did a sort of weak field or strong field. So if it's sort of in that grayish area in the middle there, and they don't sort of give you direction, sometimes it may not make a difference in terms of how the electrons are sort of distributed in those orbitals, in terms of how many non-bonding electrons or unpaired electrons that we may have. Any questions on that there? So let's take a look at sort of an example. If we had like the one coming up, I think, just to see how we get there. Let's take a look at, if we have this complex ion here, this FeF6, 3 minus. So first off, when we would look at this, the first thing we really want to think about is really our metal here. And we want to think about how many electrons there are in that metal, which means we really should figure out what the charge is on that metal. So if we look at this guy, we know fluorine is -1, and there's 6 of them, which gives us a -6. There's an overall -3 charge, which means in this case, this is iron with a +3 charge, basically. So what we have here in terms of our metal is iron with a +3 charge. If we look at iron with kind of no charge, Got iron, no charge. That is number 26 on our electrons, right? And if we do our configuration, that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 2, 4, 6, 3d6, right? R, that is argon, 4s2, 3d6. So earlier in this chapter and stuff, we refreshed our memory about what happens when something like iron loses electrons. When a transition metal loses electrons, remember it is the 4s that gets lost first because they are technically highest in energy. So if we lose the 4s electrons, that's only 2 electrons, but we have a +3 charge, which means that it lost 3 electrons. That means the next highest would be the d orbitals, and we would then take 1 out of there. And that would leave us an electron configuration really of argon 3d5. Any questions on that so far? So when we talk about argon 3d5, we're really, for this purposes here of crystal field splitting, looking at our d orbitals here for iron. And what we can see is it contains 5 electrons, which means by itself, without sort of the ligand present, if you will, iron with a +3 charge would have 5 electrons to be distributed. So what are we looking at here in terms of how these electrons would be distributed? We want to then look at really the ligand that's attached to it. And in this case, the ligand that's attached is fluorine. We look down here, fluorine is sort of heading over here to our weak field sort of side. And we will do it then as a weak field. So what that means is the distribution that we will see of these electrons will happen like so. It will go 1 electron, 2 electrons, 3 electrons. Now, because this is in this case weak field, we would assume that this splitting that's happening here between the lower d orbitals and the higher d orbitals is not very large. So we would expect those electrons to be distributed like normal. And this would be basically the electron distribution here of those d orbital electrons in this complex ion. First off, any questions on that there? Now, when we look at it, we see several things. We see 5 unpaired electrons here. And what do we also see? We see a lot of unpaired electrons. Again, electrons having their own spin. This is also what is sometimes referred to as a high spin complex. So what does high spin complex mean? High spin complex means you have a lot more unpaired electrons, as you can see here, a lot of unpaired electrons. And that is again a result of really the splitting of these d orbitals not being tremendously sort of large in terms of the splitting that's happening. Any questions on that there? Okay. Now, let's take a look at what happens as we look at the same iron sort of guy in FeCN 6 3 minus. Again, here, if we kind of take the same approach, Cn minus is -1, that's -6. Again, here we're starting with the same 3 +3 charge on our iron, which means again for our iron with our +3, just like we had previously, we're looking at argon 3d5. These are going to be the 5d electrons again distributed here in this complex ion. Now, when we look at Cn minus, if we come back, our Cn minus is over here now at a strong field. So because the ligand here is Cn minus in this case, we're going to get this strong field approach. And what that means is when we go to distribute these electrons, we now have a pretty large separation happening here. And as they get distributed, the way they're going to decide to go in is they're going to go in one, they're going to go in two, they're going to go in three, and decide this is way too high up there. I much rather than go in four and five. In this particular case, when we look at the distribution, we actually end up with one unpaired electron. And that is what is sometimes referred to as a low spin complex. Low spin because most of the electrons are paired up, right? When they're paired up, kind of their spins cancel each other, right? So they're not kind of spinning around. When they're unpaired, right, they have their own sort of spin that's happening. Nothing sort of counters it. But when we start to add in those kind of paired electrons, right, which is what happens when two electrons go in the same orbital, they sort of cancel out their effective sort of spin that's happening. And again, that goes to sort of that spin quantum number of, if you remember, it's either plus a half, right, if it's spinning this way, or minus a half if it's spinning this way. And again, sort of when they're paired off, they sort of counteract each other. Obviously, when there's only one in there, there's obviously nothing to sort of balance it in terms of the spin that's occurring. Now, for both of these sort of guys that we looked at, they both have a coordination number of 6. They both would do the octahedral splitting, and they both actually have the exact same sort of charge in terms of the metal that's in the middle. The difference, though, is how these electrons are going to be basically distributed in this case. Any questions on that? So also going back to the idea where I said, sometimes they may even ask you, do it for strong field or weak field. They may also sometimes ask you to do it for like high spin or low spin. So that's another sort of way that sometimes you're asked to sort of distribute these electrons. And again, obviously, high spin would be a small splitting. Low spin would be a larger splitting that's occurring. Any questions on that one there? Okay, so why don't we try? Let's try one here. Right? Why don't you do the diagram for? Let's just do. Let's try the one we just did or just saw. Let's do this guy. And let's do this one here. So do both of these. Do the draw the crystal field splitting. That's these arrows and stuff, and also figure out how many unpaired electrons there are. I'll do it too because I just made it up, so we'll see how we did. So take a few minutes to see what you come up with. By the way, cobalt is number 27 on the periodic table. Look at this and sort of see how you're doing. So again, the first thing you really want to do is figure out really how many electrons you have to distribute. And let's take a look at the first one here first, I think. Go back here. Whoops, come here. There we go. So we have this guy here, which is this again, just so reference sake, this is coordination number 6, right? As NH3 is monodentate. We also then, is probably octahedral, which will give us our octahedral splitting that we've been looking at, which is basically these 3 d orbitals here are XY, YZ, and XZ, and up on top, which would be R squared, guys, basically. And we also want to figure out, again, the cobalt here. So Na3 is 0. That means cobalt here is +3. Again, cobalt with no charge is 27 electrons, which would technically give you argon 4s2 3d7. Again, with the +3, that means we're going to eliminate those two. We then also will need to take out one of those guys as well, and that would give us an argon 3d6. Any questions so far? All right, at this point, what that means is we want to basically distribute those 6 electrons, right? So the 6 electrons is basically what we have to distribute. Again, in the absence of the ligand, they would all just sort of line up like normal. So we do need to look at our ligand here. And again, our ligand is NH3. And if we look back at our sort of series, NH3 is over here. It's probably leaning maybe towards more strong field. Again, since they didn't really kind of give you any information, you can probably figure it's more strong field than probably weak field. Again, if they gave you some more specific information, like do it one way or the other, you could probably make that judgment. So what we'll do is with strong field on this one, because of the NH3 here, we'll do it for strong field. And what that means is strong field means we're going to have a large crystal field splitting that's going to happen over here. And that is, again, going to affect how these electrons get distributed. That means that these electrons here would get distributed as such. It will go 1, it will go 2, it will go 3. It will decide they're way too high up there. We're going to go down first, so we're going to fill up these lower d orbitals. And at this point, I think I just hit all 6 there, if I'm not mistaken, right? 1, 2, 3, 4, 5, and 6. Any questions on that? That would obviously mean we have 0 unpaired electrons. This definitely would be what is considered a low spin sort of complex. Any questions on that there? Now, again, looking at the other one that we saw there, cobalt Br. So let's go here. This cobalt Br6. 3 minus. In this case, bromine is -1. There's 6 of them, so that's a -6. So again, here, our cobalt is going to be +3 in this case. Coordination number also 6. Also going to do our octahedral splitting of our lower d orbitals. And our higher d orbitals here, which will be our squares. All right, so really coming out the same as what we just saw there, we're going to end up again with argon 3d6. Again, we're going to have those same 6 electrons to distribute in this case. And now we want to determine, is that distribution going to be different or kind of the same distribution as what we just did? Again, here we would want to look at bromine. Going back to our spectra series, we definitely see there's probably no doubt on this. Bromine is far left there and would be weak field in this particular case. And that means that the Br is going to be weak field. And that means that the separation here is going to be small. So how that affects our distribution of those same 6 electrons that we just dealt with previously in the other complex ion is it will go 1, it will go 2, it will go 3, and decide that's not too bad. 4, 5, and then 6. So here we end up with 4 unpaired electrons. And again, that would mean that this is a high spin complex. Again, with those four sort of unpaired electrons that are happening. Question on either of those sort of examples. Now, again, in some cases, like I said before, it may not make a difference, as to sort of which way you go in terms of distribution of those electrons, depending on what you have to distribute. So, for example, if you had, let's see, let's try to do it off the top of my head here. Let's say we had, nickel here, and let's say we did nickel. And we'll do a +2 on this guy. All right, so if we look at this, right, water here is 0. Again, this is obviously a coordination number of 6. This would also give us, again, our octahedral splitting of those orbitals, just like we did before. And now water's dead center, right? So we can, could do perhaps either one here. And let's see if it actually did make a difference at all in terms of our distribution of what's going to happen here. So this will be here, the one I'm doing. This will be our weak field. And we'll do it for strong field as well and see what happens on that. We'll draw it dramatically different here. There we go. All right, so coming back here, and our nickel obviously would be a +2 in this case. And again, nickel kind of with no charge is 28. That's going to give us argon 4s2 and looks like 3d8 it should be. With a +2 charge, that means it lost 2 electrons. It would be here. That would give us argon 3d8. So in this particular case, we would have 8 of those d electrons there to distribute. And normally, right, with nothing attached, it will look something like this. Looking at our water, again, if we look at our water, it is, pretty much dead center there. So, maybe it could be considered weak or strong. And again, probably in a situation like that, they would probably give you some type of information in the actual question as to which way to do it. But here we're just going to do it both. And hopefully, if I made this up right, we'll see what I'm hoping we'll see. So let us do the distribution of our electrons in the weak field. So that means we would want to distribute our 8 electrons. So it'll be 1, 2, 3. Weak field means not a big deal. 4, 5, 6, 7, and 8. We end up with 2 unpaired electrons. Now, if we did it for strong field, 1, 2, 3, too big. So it'll come down here first. 4, 5, bad arrow, 6. Got nowhere else to go now. 7 and 8. And looky, it did come out the same. So that was a pretty good guess. There we go. Also has 2 unpaired electrons. And that does happen sometimes. Sometimes it does not make a difference whether it's sort of strong field or weak field. And again, if it's kind of a gray area sort of ligand that's there and they really don't give you information, it may just be this situation that's occurring, that technically you could do it both ways and you'll end up with the same unpaired electrons. Any questions on sort of the distribution and how to do it? Okay, then here's sort of your different combinations that you could have, again, for our octahedral complexes that have obviously our distribution of electrons. Left-hand side is all of our high spin, which means these guys are pretty much weak filled, which means small separation. Over here's our sort of low spin, which basically means that it is typically strong filled. We're going to pair up everybody first, usually a larger delta sort of happening. And again, on the left-hand side, we have a lot more unpaired electrons. Right-hand side, not as many unpaired electrons, again, giving us that distinction between low spin and high spin. So what we've been talking about up to this point is the kind of splitting that occurs when we're dealing with an octahedral complex. And that is, again, as we talked about, our coordination number of 6. Now, what happens is we're not dealing with sort of a coordination number 6 or that octahedral sort of geometry or splitting or complex. We can have some other ones. So this is what occurs in our tetrahedral complex ions. These are guys with our coordination number of not 6, of 4. Try that. So that's our 4sp3 sort of splitting that's going to occur. Works exactly the same way as what we've just been talking about. And actually, the difference is they're kind of opposites of each other. So if you remember, in octahedral, these 3 were on the bottom, and these guys were on top or higher in energy. We get this opposite sort of splitting that occurs in our tetrahedral complex, but same sort of results. Again, if we're filling these guys up and the splitting is not that large, we will just continue on like normal and start pairing people up. And just like we talked about on the previous one, if we do get down to here and decide that the splitting is relatively large, we will pair up first and then come upwards again and sort of distribute those electrons into each of those. So kind of works the same way. Same idea, looking at really what ligands are attached as to sort of the difference in splitting that's going to occur between those guys. Any questions on that one there? And again, obviously, this is for something that would have something like 4 ligands attached, and again, a coordination number 4. Another coordination number 4 is our square planar. And again, this geometry here, a little crazy in terms of how the splitting is occurring. We got kind of our 2 guys there, then this guy, then this guy, and then this guy. So some of that weird sort of splitting that's occurring again is more of a expanded sort of octet. There's some of those extra electrons in a way, and again causing a little bit more distribution of those individual sort of d orbitals that we see. For us, you will be responsible for octahedral. So you need to know octahedral splitting and tetrahedral. We'll leave square planar off, so tetrahedral. So you need to know those 2. We'll leave off square planar. Any questions on any of that there? So that concludes sort of this chapter on complex ions. We're actually going to go now back, I believe, to chapter, you guys, I believe that's chapter 16, I think, in your book. So there's that one section in chapter 16 that we kind of skipped over when we were talking about KSP. We're now going to go back to that one because it does relate to complex ions and equilibrium involving complex ions and some of the stuff that we do with it. That's a little bit different than some of the calculations we do with other things. So technically speaking, we're now going to drop back to this should be chapter 16. Any questions on any of that there? Okay, so again, I almost want to say a 16.3. I could be wrong, but off the top of my head, I believe this is 16.3. It should be the section that comes right after KSP. So it should come right after KSP. All right, so what we're going to talk about here, again, in sort of the last little bit of this chapter here, is basically, like I just mentioned, equilibrium involving complex ion. A complex ion, as we've been talking about, obviously, contains really a central metal, central positive metal, a lot of times a transition metal, something with a kind of a large positive charge. Um, and a number of ligands are attached. So as we've been talking about, obviously, ligands are Lewis bases, which means again they're going to donate a pair of electrons. And as we were talking about before, sort of you can think of our metal as being more like the Lewis acid. It has a positive charge, usually a pretty good positive charge, again, meaning that it's fairly electron deficient, willing to accept those electrons. So, in order the formation of this, we can set up our metal here plus our ligand and make it our complex ion that now you know how to properly name something like that, right? Uh, you know, tetrachloral cobaltate 2 ion, something like that, right? So we learned that last time. Um, and it will set up an equilibrium. Because it sets up an equilibrium, we could not miss talking about K with our complex ions, and it forms what is referred to as Kf, which is basically the formation constant, and it's really the equilibrium constant for complex ion formation. And again, we do it like any other K value that we've been doing. It's our products divided by our reactants. Just like normal, if we got a coefficient, it is going to be obviously our exponent. So we do this exactly the same sort of fashion. What we will see is Kf values are really large values typically. Because they're really large values typically, what that means is when we get a ligand near a metal, and they definitely would want, or a good ligand, I guess you put, near a metal, they definitely would want to form the complex ion. So because they're really large, so large that it's almost a one-way street heading towards our complex ion being formed. So they're very large numbers. We'll see a table a little bit later on here, but you will see values that are very, very large. Because ultimately, though, it is a equilibrium constant value, the Kf, we could treat it like a normal equilibrium constant value, which means if we have a large value of K, our Kf increases, the stability of the complex ion also increases. So what does that mean? Well, it means obviously if we have a large value of K, we would expect when we reach equilibrium to basically have products. And when we look at our reaction here on our product side is where our complex ion is. So again, as we see the Kf value increase, we see basically the wantingness to form a complex ion, and we see it basically moving that sort of equilibrium to the right in the formation of the complex ion sort of happening. As we just talked about as well, obviously the metals and their charges and also the ligands attached do give them some different properties, absorption sort of values. And obviously you can see here, we see one is more of a pink, where cobalt there is attached to water in its +2 form. And when it's attached to chloride there in its +2 form, we see a more bluish type color. Also, if you think about these difference between these two, one has a coordination number of 6. We're just going to give a more octahedral splitting. One has a coordination number of 4, right? And that's going to give you more of that tetrahedral R square planar sort of splitting. Again, we see some of those differences in terms of colors that appear in our solution. A reminder, since we just talked about this not too long ago here, things that are good ligands are really things that are polar. They have non-bonding electrons. So things like water obviously is very good. It's got those non-bonding electrons on the oxygen. NH3 has got the non-bonding electrons on the nitrogen. Obviously, things that have gained a negative charge usually indicates that they have gained more electrons. um, and that's why they're negative. We also talk about the number of atoms directly bonded to our metal in our complex ion. And again, that is what is referred to as we've been talking about the coordination number. As we talked about in the last chapter, that obviously is also dependent on the type of ligand that's attached. So again, remember we have some that are monodentate, which means again they bind one per sort of ligand, if you will. We have some that are bidentate, which, again, bind two per ligand, right? Things like our endoethyl diamine, that's like a 2-for-1 situation. We also have oxalate that we saw, also like a 2-for-1 situation. Every one of these molecules will bind in two places per molecule. Again, basically doubling your coordination number if you're counting it up. We also saw things like EDTA, which basically does like a 6-per-1 sort of binding situation that's occurring as well. Now, also important, especially important for sort of the idea of what we're going to be talking about here, which is sort of KF calculations and calculations involving ligands, is they do basically come on or attach one at a time. So, kind of similar to how we talk about polyprotic acids, for example, that they lose their hydrogen basically one at a time. And if you remember, there was like a K value or Ka value for each of those hydrogens that basically come off. And the same thing happens when we're dealing with complex ions and ligands. So, for example, if we were looking at this guy here, which I think we just saw the overall reaction just a second ago, it actually does occur in several steps for that formation of that complex ion to occur, even though we sort of look at the overall reaction. The first thing that's going to happen is basically we would take one cobalt ion and basically one chloride ion would attach, and we would get something that looks like this here. And this would have a kind of K1 type of equilibrium expression that would occur. The next thing that would happen is that guy that has now gained one chloride will then gain another chloride here, getting us to COCl2. Again, also going to have a K value basically happening for that equilibrium. Just like with our hydrogens, the next thing that would happen is this guy would then pick up another chloride, giving us COCl3 minus 1. Also, again, a K value associated with kind of that step. And the last thing that would happen is this guy here would pick up its last chloride. And we will end up with this guy right here that would also have a K expression that would go with it as well. So again, it's sort of this stepwise addition of these ligands that basically occur. Now, this is also how we get to sort of that overall reaction that we were just looking at. Again, if we add up all these guys, we basically could cancel out, just like we normally do, anything that's the same on opposite sides of the arrow. This guy would cancel, this guy would cancel, this guy would cancel. And that would leave us our overall reaction that we just saw on the previous slide, which would be our cobalt, plus our, if we just go on the left-hand side there, 1, 2, 3, and 4 chlorides that are happening, plus makes our COCl4 2 minus here. Any questions on that there? So how would we get the KF value for this guy if we were given sort of these 4 steps that are occurring? Well, just like we talked about when we were talking about just regular equilibrium at the very beginning, when you add up individual equilibrium reactions and you want the K value for the overall reaction, Remember, we don't add them here, but we actually multiply them. So we take K1 times K2 times K3 times K4, and that would give us our equilibrium constant for the overall reaction. So ligands do get attached kind of in a stepwise fashion, and that's really important for understanding some of these calculations that we're going to talk about here in this chapter, or the rest of this chapter. Any questions on that? All right, so since we're getting to the end, we will need more time than that's what's left to kind of go through this first example. We will stop